This work presents and implements a practical method for balancing illumination in images from various sources. Uneven or inadequate lighting can lead to loss of detail, reduced contrast, and inaccurate color reproduction. Overexposure may cause bright areas to lose detail. This challenge is especially relevant in medical imaging, where insufficient lighting often results in dark images, making it difficult to see important detail, particularly in shadowed regions. We analyzed unevenly lit images by studying their gradient fields to enhance visual quality. To tackle this, we examined traditional computational approaches for solving second-order elliptic equations in mathematical physics. We then developed a model using the Poisson equation, applying the variational principle. Numerical methods were employed to solve the model, and we evaluated their effectiveness by testing on different images. The issue of image illumination concerns how light impacts the quality and perception of an image. Insufficient or uneven lighting can cause detail loss, low contrast, or inaccurate color representation. Overly bright lighting may result in areas where details are lost due to excessive brightness. This challenge arises in medical imaging, where insufficient illumination can make the image appear darker and obscure important details, particularly in shadowed regions. A key issue is uneven lighting, which complicates the accurate perception of objects being studied. To correct unevenly distributed lighting in the image, you need to preserve all boundary elements of the objects that are in the image under study. In order to distinguish one object from another, it is necessary to have data about the gradient of the entire image, which is presented in the form of two matrices for each channel. If the image is full color and is presented in digital form in the RGB palette. The Poisson approach involves saving this information on the basis of such a quadratic functional I1 of u, which must be minimized. It is obvious that in order to equalize the unevenly distributed illumination in the image, it is necessary to minimize another functional, which has the form I2 of u. The functional I2 of u focuses on minimizing the variance. Reducing variance leads to a more uniform distribution of pixel brightness across the entire image. Here, the functional represents the variational formulation of the problem aimed at correcting uneven illumination. By solving this, we achieved the desired result, which is I of u. This variational problem can later be transformed into its differential form by applying the Euler-Lagrange equation. And after simplification, we get the Poisson's equation. You can set u hat to 0 to ensure a unique solution, which can then be constrained within the permissible pixel intensity range from 0 to 1 for real numbers or from 0 to 255 for integer values, using the classic formulas. In the first equation, we assume the existence of a known function f of x and y. Consequently, the derivative delta f can be computed using established classical difference schemes. The boundary conditions for equation are characterized by the equality of zero derivatives. To write the difference equation, we will apply central difference schemas at each node. By transforming the equation and gathering all the coefficients corresponding to the different points, we can derive the 5-point difference scheme for the equation in the following notation. Now here you can see the results we got for image 3, which has around 47,000 pixels, and image 5, which has around 49,000 pixels. What we can see from the plot is that the Tidal method performs poorly, especially at lower lambdas, resulting in longer computation times. This work presents a comparative analysis of unevenly lit images using gradient fields to achieve visual enhancement. Mathematical dependencies for approximating the solution to equalize pixel intensity were developed. Classical second-order elliptic equation methods foundation of the variational approach in Poisson image processings were analyzed. Zeidel's method performed worst in terms of time, while the block run method with Python's SciPy library performed the best. Multi-grid methods are recommended for improved time efficiency as they reduce iterations. Additionally, calculations are faster when performed in a normalized system where values range from 0 to 1, rather than the classic where values range from 0 to 255. Thank you for your attention.